So I'm Aleks. I'm going to talk about how to hack a cryptocurrency client. What I'm going to cover here is, first I'm going to talk about like what the typical Satoshi blockchain client looks like, what's in there. Then I'm going to talk about the most common security issue types for this type of clients, and then I'm going to kind of go in detail talking about some net split and fork attacks that happen in Bitcoin, and also talk about some application level DoS issues if there is time. So I'm not going to talk about smart contract hacking. I'm not going to talk about privacy preserving crypto, such as stuff like crypto in Zcash and Monero and stuff like that. And I'm not going to talk about the alternative consensus algorithms. There is now a race who is going to make a scalable blockchain, basically many transactions per second. That's the goal. So what's the goal here of this presentation really is to provide an idea what basic blockchain vulnerabilities look like. So this is a time machine. I'm going back 11 years ago, or maybe not 11, but maybe 6 or 7, when Satoshi published his paper in 2008, and then the community found some bugs, and they keep on repeating. So that's the goal here. So if you want to audit a blockchain software, this presentation I hope is going to be helpful. Or if you want to re-implement a Satoshi client or some new generation blockchain client. So some people seem to think that aliens have created Bitcoin. That's fun. In October 2008, it was published, the paper was published, and the implementation came 3 months later. It was only for Windows, but then I think about 6 or 7 minutes, not minutes, but years, not years, but months later, it got ported to Linux. So what's the idea here? The idea is to have electronic cash without any central authority or any financial institution. So if someone wants a decentralized system, it's kind of natural to try with a peer-to-peer network. So what's really the main question that the Bitcoin paper tried to answer is how can nodes in a peer-to-peer network establish a synchronized view of the ledger? Essentially the main novel idea in the Bitcoin paper was how to establish consensus via the proof of work concept. So plug in proof of work concept for the purpose of synchronizing the ledger. Over the last 11 years, the Bitcoin community did a huge amount of work. So they maintained and refactored the code, changed existing features and added new ones, and also uncovered a fixed number of important security issues. The original Satoshi implementation was solid, but still there is a bunch of issues that got uncovered. So if you're auditing or implementing a blockchain client, it makes sense to kind of process what happened in Bitcoin in the last 11 years. To rely on their experience and to avoid the same things, because these things keep on repeating. If we try to kind of look at what's happening in this area, it's really, there's a lot of implementations, but we could come up with some criteria how to differentiate if we take like a random blockchain project out there. At least some features we can definitely discern what this is about. So it could be a permissioned or permissionless blockchain. If it's a permissioned one, that's typically aimed to be deployed inside banks or some kind of financial institutions, and all nodes authenticate each other. And oftentimes this is actually centralized system where there is one central authority with some accountability to its clients. So this is actually usually not Satoshi blockchain. There is no proof of work, and there is no decentralization in the degree there is in Satoshi blockchain. So then we can take a look at what kind of smart contract capabilities this kind of imaginary product we're looking at has. So it will have a Turing complete language. So this would be Ethereum, for example, or it have kind of minimally expressive or inexpressive smart contract language, which is aimed to be secure but is not really expressive. So this will be Bitcoin, and Nowadays, it seems that like the trend is to try to aim between these two, not have a Turing complete language, but have something really kind of in between these two. And also then we could ask what's the consensus algorithm the nodes are using. So this could be, for example, proof of work or proof of stake or some kind of adaptation on Byzantine fault tolerance algorithms. This is coming from distributed systems research, and the main problem there, it does not scale to many nodes, and then the scalable blockchain solutions that are racing to deliver a novel blockchain solution are kind of trying to adapt on this and change BFT algorithms to scale. And also we could ask if it has fancy crypto inside, such as Zcash or Monero. So now, when it comes to security researchers, let's take a look how well researched are these types of products. So permission blockchain, there's zero research most likely. So these projects aren't, many of them are not finished yet. They're still being developed. Most of them are not open source. This is proprietary software. And really, the security of these systems is not well understood. On the other end, smart contract hacking is quite popular. Lots of companies offer smart contract review as a service, so it's a kind of niche consulting area, smart contract review. There's also static analysis tools which are supposed to do this automatically. And then if we take a look at what consensus implementation, how well understood are consensus implementation issues, well, they're understood very well by the Bitcoin community. But as for security researchers, it's kind of under-researched, I would say. Yeah, maybe this gap should be filled. Yeah. So let's take a look kind of mechanically. What does a blockchain client do? Satoshi blockchain. So it listens on the network for new protocol messages. Typically, this is not something like REST API. It's more usually some kind of custom protocol. It ingests transactions and blocks. So nodes send transactions and blocks to each other, and each node validates them. They store a copy of the ledger, basically who owns what at the moment. They contain capability to mine new blocks, and they kind of do that if they're full nodes. And also they try to be in sync with other nodes. Every node would, should see the same ledger as other nodes. So there's this distributed idea of what the current ledger is, and it's kind of consistent over all nodes. Yeah, so this is a complicated list of tasks, and if someone tries to do all this, it's likely that some mistakes will creep in. So if we take a look in a little bit more detail, what a blockchain client does, well, the state it keeps is it wants to keep the ledger, obviously, who owns what, and it keeps blocks. So there are blocks. Blocks contain transactions. Each transaction, so for example, there may be actually this is B2, should be B3, B4. So each transaction actually points to a previous transaction whose coins it spends. So yeah, transactions point to previous transactions, and each block points to a previous block. So this is a sequence of blocks, and the ledger is actually what's currently the transactions that have not been spent yet. So that's our ledger essentially. So now since the nodes can actually everyone can post blocks on this network. There is nothing to enforce that the blockchain will look like like a line in this picture. In fact, participants can post these blocks and have multiple blocks pointing to one previous block. So actually, nodes keep a block tree. They end up keeping a block tree, not just a blockchain. And for each node, the blockchain, actually the ledger, is a branch from the genesis block to one of the leaves. And now, if that's called kind of the active branch. We could call that the active branch. In theory, a node could also switch to a different branch. For example, it could have B4 be the final block here, and Genesis B1, B3, and B4. So now, when it comes to this block tree, if we assume that all nodes in the network see the same block tree, so these blocks get broadcasted, and they should, assuming good network conditions and no major discrepancies in the state and implementation of the nodes, all of the nodes should see the same block tree. The question really is how do we decide what's the active branch? What's really the ledger that we kind of believe in currently? So we need to come up with a criterion. What is going to be the ledger from us from all these branches? And this criterion should be resistant to manipulation. So I should not be able to make nodes kind of arbitrarily switch branches in a block tree, because then I'm going to change the view of what the ledger is for other nodes. So switching branches in this block tree should be somehow controlled. And the reason also is to prevent a double span attack. So what's a double span attack? Well, the idea of a double span attack is to create a transaction that's going to spend some coins in block B4, and then revert, basically switch to a different branch, and the transaction gets reverted. So in a bit more detail, in Bitcoin we have a 6 confirmation rule. So a transaction, suppose there is a transaction in block A1 which gets confirmed in block A6, and then the whoever sent the transaction can exchange it for goods or services, and then the attacker publishes another branch which does not contain this transaction at all, and the effect of transaction gets nullified, and he can spend his coin in this B branch. So that's the idea of a double span attack. Yeah, so really a lot of the Bitcoin paper motivation is how to defend from the double span attack, how to really control switching branches in this block tree. And to come up with a solution to that, the Bitcoin paper proposes to use the proof of work puzzle. So proof of work is just a puzzle that's easy to verify but difficult to solve. So we can use a hash function to create a proof of work puzzle. For example, we can ask basically we can require for an input to the hash function to be found such that the output has some number of zeros in the output. Yeah, so the Bitcoin idea is really to kind of control switching branches, making nodes switching branches by leveraging the proof of work puzzle. So how does that work? Well, if someone wants to add the block on this block tree, then he needs to solve the proof of work puzzle at a certain difficulty. So now an active branch will be considered the active branch. The ledger will be considered the branch with most work. And work, so we can kind of calculate how much work has been put in this branch. And if that amount of hash work or proof of work puzzle work is more than other branches, then that's the active branch. So now if I want to make another node switch to a different branch, switch to a different ledger, I will have to attach more blocks here, for example, B4, and then I need to invest computing power in that. And whether I'll be able to do that depends on how much hash power exists in the network overall. So this places control over how difficult it is to switch branches in the block tree, or how difficult it is to manipulate the other node's view of what the ledger is. And that's basically the main idea of the Bitcoin paper. So yeah, now zooming out a little bit, what do we have in the Bitcoin CVEs last 11 years? So there's around 30 of them. It's kind of reasonable to say that probably many of the issues that have been found never made it into CVEs and maybe have been silently fixed, so no one even knows about them. But at least this is some kind of approximation of what the bugs looked like in Bitcoin. So there were 14 DoS attacks. So in DoS attacks, this would be kind of application security DoS attacks, meaning, for example, crashes due to a division by zero or some assert failures, or CPU exhaustion. So someone sends some kind of block to a node, and the node ends up processing it forever and cannot ever stop processing it. Also memory filling out the memory of nodes, stuff like that. Yeah. So then there is net split attack. So net split attack would be when one part of the nodes of the network see one ledger or active branch, and the other part of the node see another branch. So we're going to go into detail with that. There is theft attack. So theft would be something like, it could be either theft on the blockchain itself, meaning that during validation, simply the blockchain accepts invalid transactions and, for example, creates coins out of nothing. Or it could be some localhost API and wallet issues. And there are also some others, such as inflation. That's actually interesting. Inflation is when you create coins out of nothing and then the value of the coins drops and stuff like that. So I'm going to talk about net split attacks next. Actually, before that, so yeah, this is the Bitcoin CVE list. And if we kind of try to not only focus on Bitcoin and try to come up with like OWASP top 5 of vulnerabilities in kind of Satoshi blockchain implementation, not only Bitcoin, but whichever other coins are similar to Satoshi blockchain. This could be the top 5 list. So let's start from the last one. Localhost wallet API issues. If I run like a kind of any coin node client, it's likely going to open a localhost wallet API for managing the wallet. And issues around here are lack of authentication, course header issues, CSRF, and stuff like that. Cross-site request forgery and this type of attacks. And then there is appsec and network API issues. So this is all possible issues that come with appsec. So it could be memory corruption, denial of service, serialization and deserialization problems, and so on. Improper timestamp validation. So improper timestamp validation, every block has a timestamp. And why is that? Well, timestamps inside blocks are used to control the difficulty of mining. If blocks come in too often, then this means that the difficulty of mining should be increased. And that's why every block has a timestamp. And now when nodes are processing blocks, they need to validate this timestamp. And this, well, it's not super hard. It's not trivial either. And coins routinely get this wrong, and they just do a very first thing that comes to mind, timestamp validation. Instead of that, they should look how Bitcoin or Ethereum do it and do it that way. And this results in net split, also chain wedging, and mining difficulty manipulation. It's kind of a bug that's easy to find. There's also integer underflow and overflow. That's very common. So transaction amount arithmetic, when nodes are validating transactions, they need to add or subtract some kind of number representation, such as integers, and also if there is a notion of gas in the coin, then the same holds for that. And integer underflow and overflow do things like they allow creating billions of coins out of small transactions and stuff like that. So they're very bad. And there is net split attacks. So this is when the view of the ledger gets split across the nodes. So there are several reasons. It could be unintentional soft or hard fork. So if I'm updating a client that I have already used in the network and the whole network is supposed to update it, then An unintentional fork would be something like I'm not expecting the consensus rules to be changed, and yet they do change. And then some nodes that have not updated can't process my transactions, and there is a net split as a consequence. Now, yeah, there's other reasons, so we'll go in detail through the block, transaction, hash poisoning, and Merkle tree issues. Yeah, so this is the net split conditions. How could it happen? Suppose the tip of the blockchain is block x0, so there is no net split until block x0, and then comes in A1 and some blocks after A1, and they get validated and integrated into the chain. However, due to some reason, nodes B can't really process this block A1. It could be they could be in different state, or they may be using like a different implementation. For example, A nodes may be using a C++ implementation, and B nodes are using a Python implementation, and they don't exactly agree on what a valid block is. So now at this point, nodes B rejected block A1, and as a consequence, they also rejected block A2, A3, and A4, and they can't really do anything with this chain. So for them, the tip of the blockchain is block X0. And then, since they have mining capabilities, they just mine from X0, since X0 is their last block. And then they mine block B1 and B2 and B3. And so one part of the node sees the A chain, that's the A nodes, and the other part of the blockchain sees the B blocks, and this is the B nodes. And there's a split. So now the question is like, is this situation going to self-heal? Are all nodes going to start looking at the same blockchain or not? So this is going to happen only if chain B outpaces chain A, because nodes B can't really switch to chain A because they don't accept the A1 block. However, nodes A could switch to the chain B, because there's nothing wrong here. It's just the fact that chain A is stronger than chain B. So if there is more hashing power in chain B, then the situation will heal. If not, then the split will be permanent. So now this net split condition looks like a denial of service condition that's causing confusion, but it's kind of important to understand that the net split condition actually facilitates the double spend attack. So what's the general idea? How would we execute a double spend attack when there is a net split? Well, execute the transaction on chain A, wait for confirmation, could be 6 blocks, for example, and then this chain will be dropped at some point when the network heals or there is an intervention, and the transaction that was spent on chain A simply disappears. And now it's kind of nullified. However, it's not that simple. The assumption is that the same transaction will not cross this kind of invisible line here. It will not go to chain B. If we executed a transaction on A with some nodes, what's to guarantee that it's not going to be executed on other nodes? If we broadcasted that transaction, there is really no network barrier between these nodes. So this transaction may likely just move to the chain B as well and gets integrated in chain B. So the attacker doesn't really achieve anything. So how could we try to prevent that? If we broadcasted that transaction, then this transaction is going to go to the chain B, so we don't want to broadcast it. We could try bribing some miners to include that transaction in block A2, for example, and not only bribing, I think some miners offer that as a service. Maybe I'm wrong there, I'm not sure, but you can just ask them to include your transaction without revealing it to other nodes. However, even then, if we just include that transaction in block A2, the transaction itself is visible, and it's public, and it's signed by the cryptographic key of the originator of the transaction. So someone from the B network could just take that transaction out of block A2 and post it to network B. So to bypass all those problems, one could try mining the transaction privately on chain A by making a miner include his transaction or her transaction, and at the same time, as soon as this transaction is mined, broadcast a double spend. And if a double spend, basically the double spend is going to spend the same coins that the transaction on the A chain spent, and then we can't really replay the transaction from the A chain because the coins have been already spent. So so the point here is that net split is not only a denial of service condition. If someone manages to perform a net split on the cryptocurrency network, he can steal coins. So let's look at how would it be possible to cause a net split condition. There was a CV. So the one typical way that comes up in cryptocurrency clients is via block hash poisoning. So what's that? When nodes process blocks, since this is a peer-to-peer network, the nodes want to do this only once. So once a node receives a block, the hash gets cached, and in future the node is going to reject processing this block twice. So yeah, I send the block to the network, and regardless if it's valid or invalid, the node is going to process it, and once it's processed, the hash is going to go into a hash list of processed blocks, and if I resend the same block twice, it's not going to process it anymore. It's been processed. So the idea here really is to poison a valid block's hash. So an attacker listens on the Bitcoin network for new blocks, and then tweaks the block content to invalidate the block without changing the block's hash. And then the nodes that received the tweaked invalidated block are going to deem it as invalid and cache basically the hash of that block and not process it ever again. So yeah, once again, the main idea here is to listen on the network for new blocks, and as soon as a new block is broadcasted, before it reaches all the nodes, you tweak the block without changing its hash, but that invalidates the block, and you quickly try to broadcast it to some other nodes. And if they receive that block first, which has been invalidated, you have kind of squatted on the valid block's hash, and these nodes can't really anymore process valid block's hash. And that's really the situation here with A1 block. For example, nodes B have already received invalidated block A1 with the same hash, and they refuse to process it. So now the question here really is block hash malleable? Can we take a block and change something inside the block without changing its hash? If we can do that, then we can perform a net split attack on the network. So what's in a block hash? Well, this is probably not Bitcoin, but looks like Bitcoin. There is there's a couple of fields here that get hashed. So there's a previous block hash, nonce, timestamp, and transaction merkel root. So previous block hash is the pointer to the previous block. The nonce is used to solve the proof of work puzzle, and there is a timestamp, and there is the merkel root, which is nothing but really a digest of transactions in that block. So yeah, every block has transactions, and we, instead of kind of directly hashing the transactions, we hash the merkel root of the transactions, and these are transactions. So this block will have like 4 transactions. Example here, T1, T2, T3, and T4, and in order to compute the merkel root, we hash T1, T2, we hash the leaves basically, and then we concatenate these hashes and hash them again, and we do that pairwise, and we then do the same for these inner nodes and get the root. But it's not really important how this works. What's important is this is a digest of all the transactions. So now, what our goal here is to change something here so that the hash remains the same. That's actually the attacker's goal. He's trying to invalidate the block without changing the hash. So now what we have here is actually a multi-field value. So we have a couple of fields here, 4 fields that need to get hashed. So if we're hashing like a multi-field value, we need to come up with some serialization function. We need to somehow convert these 4 fields into a byte string. And so we need some kind of serialization, so that's denoted with serialization here. H is the hash function, and we serialize these 4 fields. And also, here in the picture we have 4 transactions, but what if we have 3 transactions? Then we are going to have a missing field here, and we'll need to come up with something to put here, because we can't compute the Merkel tree if the number of transactions is not 4 or 8 or 16 or a power of 2. So that we denote with the pad function. We need to pad transactions so that the number of transactions is power of 2. If we're looking for a collision, a hash function, like just a pure hash function, that's hard to have, or not doable. However, we're not dealing with a hash function here. We're dealing with this whole construction. It has serialization and it has padding. And so suppose, how would an attack look like if on the serialization function? So let's try to exploit the serialization function for the purpose of obtaining a collision on this whole block hash. So suppose that serialization function is a really simplistic one. We're just concatenating fields. So we have these 4 fields here, and we're just concatenating them. So yeah, that's shown here. We take the previous block hash, concatenate with nonce, timestamp, and Merkel hash. So then someone could take a valid block hash and take the last character of the nonce here and just move it into the timestamp. So if we do that, then the concatenation of these fields is not going to change, because we just moved last character from the nonce into the timestamp. And that changes the fields here, and if we add a character into the timestamp or remove a character into nonce, that may as well invalidate the block, because it's going to change, for example, the timestamp, or it's just going to be a formatting problem. The number of characters in the nonce is not going to be valid. So if we take a block and we take the last character out of one field and move it into the adjacent field, the concatenation in the serialization function is going to remain constant, and the whole hash function is going to hash to the same value. And as such, we basically obtain the collision in this whole construction. This was never the case in Bitcoin, but it kind of happens from time to time. It's the point here is if we're serializing multi-field values and then hashing or signing them, we should not use plain concatenation as a serialization function. Otherwise, we're vulnerable to this attack. So now let's take a look if we can do something about that Merkel tree. Could we cause a collision through the Merkel tree? So if we take like a valid block and take its transactions, and suppose we just tweak 1 bit inside transaction 1 or 1 byte, the difference is going to propagate. The hash function output is going to be totally changed, and this is going to propagate into the Merkel root, so we can't really do anything that way. But if we look at the padding function here, that's really the weak link in this construction. So let's take a look how a padding of transactions for the purpose of Merkel root calculation works in Bitcoin. So suppose I have 3 transactions instead of 4. The goal of the padding is to make them into a power of 2. So the goal is to extend them into 4 transactions. So in Bitcoin, it's going to just take the last transaction in the list and copy it once again. Or if there is 5 transactions, it's just going to take the last 3 transactions and copy them in the end to reach to the 3, which is 8, and basically pad transactions that are needed to fill out these question marks here. So it's again a very simplistic padding scheme, and it's easy to find collisions on this padding. So if we take T1, T2, T3, the result of the padding is going to be T1, T2, T3, and T3. And if we take T1, T2, T3, and T3, well, the padding is not going to do anything. So the result is going to be the same. So here, this is a collision on the padding function, and the padding function is really used here in the whole construction. So based on this padding property, there was an attack on Bitcoin, which was a CV in 2012. Basically, the idea is to observe a block with less than 2 to the m transactions, add the padded the transactions that would be padded through the Merkel root computation inside a block, and send that block to target nodes. The validation will fail because there are duplicate transactions, but the hash did not change. And the kind of output of this is that correct block gets blacklisted. Yeah. Okay, so now let's take a look at another net split attack that happened in Bitcoin. Let's see how much time I have. Okay, so this was inconsistent Berkeley DB lock limit interactions. So this was a net split that happened during a software update. So there was a kind of Bitcoin client update that was supposed to take place, and this was supposed to be a non-forking update. The consensus rules of what's a valid transaction and a valid block did not change, should not have been changed. And what was the change? Well, the only goal was to replace the Berkeley database with the level database. Berkeley database was a database that was used early on by Satoshi, and it supports thousands of simultaneous threads, and like it's good in multi-threaded access to the database and stuff like that, but it had some problems, so the community decided to swap out this database and to move on to level DB. And after the update happened, about 60% of the nodes accepted the change and used level DB in their Bitcoin clients, and about 40% of the nodes remained on the old version and use Berkeley DB. So that was the situation, and the Berkeley DB configuration has a maximum number of simultaneously open locks that can be specified when it's configured, basically in the client, and this was set to 10,000. So until that point, processing blocks never triggered this limit. So if I'm processing a block, I'm kind of looking up transactions from that block in the Berkeley database, and it has not previously occurred that I hit the lock limit that Berkeley database configuration imposed. However, there was a block at some block height. It had unusually high number of transaction inputs in transactions, and this triggered basically this limit got triggered, and the Berkeley DB returned an error when trying to process that block, and the Berkeley DB nodes rejected that block. So that's the A1 block here, and since they rejected that block, they had to go on their own fork, and the level DB nodes accepted that block, and the split happened. So then, there was actually a double spend based on this net split condition. In the BIP post-mortem BIP, it's like a document that outlines Bitcoin changes. It's called BIP. It was claimed that it was non-malicious. I'm not sure what it means. Maybe the money was returned. In any case, it's interesting that this net split condition was abused for a double spend. Okay, so back to the kind of, if we zoom out a little bit from these details, net split condition means that part of nodes see one ledger and the other part of nodes see the other ledger, and this is an unexplored area of research, in my opinion. So it's a good thing to look at. So what could be the reasons in general for net split attacks? So there could be different client implementations acting on the network. For instance, I may be running a Python implementation of a coin, and someone else may be running a C++ implementation on the coin. And the question here is really, are we sure that my C++ implementation of the coin really has the same notion of what a valid transaction and a valid block is as the Python implementation? If there is an edge case in which my C++ implementation is going to accept a block and the Python implementation is going to reject the block, then we get a net split. And the problem with net split, it facilitates double span attack. So kind of interesting research topic is to take like any coin you want to take and look for different implementations in different languages and come up with edge cases where one implementation would react one way and the other implementation would react the other way. So to have like full security against net split attacks in this scenario, we need to have full equivalence of the two implementations, which is a hard requirement. So what else? Yeah, execution environment discrepancies. Well, even if there is no multiple implementations running, even if I have just my, for example, C++ implementation, then it may still be running on different operating systems, on different architectures, like 32 or 64-bit. And there may be some kind of, I don't know, there's some differences that I don't know about currently that are going to make the client behave differently. Or it may, the client may use some kind of undefined behavior, for example, undefined C++ behavior, which will turn one way on one system and turn another way on another system. Also, if I download or make a client that on my own, the question is whether it's going to use the libraries that are available in the system or it's going to fix the version of the underlying libraries it uses. So if my client uses OpenSSL version whichever and the other system uses another OpenSSL, there may be a difference, there may be a fork in these OpenSSL libraries. So that may be that may yield an edge case, which is going to make one sort of clients behave one way and the other type of clients behave other way. And then it will be a source of a net split attack. And finally, when we have client software upgrades, so the developers roll out a new version and it's claimed that this new version does not change any consensus rules. But it may look like it does not change any rules, but does it not really change the rules? I guess that's a problem for research. For example, in this Berkeley DB with level DB case, it looks like if you swap out one database software with another database, things should not change, but yeah, things could go unnoticed here. Yeah. Okay, so so if you now take a look at what DoS kind of application security DoS attacks look like, they're most numerous types of attack in this kind of environment. They can be categorized, so they're pure crashes, stuff like assert failures or divide by zero. There could be CPU exhaustion. So for example, if I send a transaction that makes other clients validate hundreds of thousands of signatures, that's likely going to exhaust the CPU of those nodes, whichever. If these clients are just operating some difficult computations, and an attacker can make them do arbitrary amount of computation, that's a problem. There was problems with Orphan transaction handling, so processing blocks and transactions is kind of involved. So it's kind of likely that DoS vectors will happen while transactions are being processed and blocks are being processed. There's also memory and space exhaustion. This is very simple. You just upload a ton of data continually on the network or on the client, and it kind of runs out of memory. And also network exhaustion here. The network starts forwarding spam and huge amounts of data between the nodes. network exhaustion is also kind of dangerous, since it often means that the whole network will start forwarding junk data across. So now if we compare DoS in blockchain, like a Satoshi blockchain in Bitcoin, with DoS in other software, yeah, DoS is regarded as a kind of issue that's not that important. So for example, in web app, it affects availability, which is a huge issue if this is like a really important web app, but it does not affect other security goals. So it does not affect confidentiality. So for example, I mean, if I have a DoS attack on a web app, I'm not going to see the passwords of users inside that system. However, DoS in blockchain is different. So DoS in blockchain results basically if you crash nodes such as nodes that mine new blocks, then effectively the network's hash power is reduced, and then there is less security against the double span attack. So in blockchain, DoS kind of gets this new power, and it's more powerful than elsewhere. It allows people to, it basically reduces security against the double span, and double span really is the main, resistance against the double span attack is the main point of blockchain, Satoshi blockchain. Yeah, so DoS vectors have higher severity in blockchain. Let's take a look what's here. CPU and memory exhaustion bugs. So how could we, what would be the source of a CPU exhaustion bug? Well, whenever we expose an algorithm, which is a quadratic complexity algorithm, such as we have a bad sorting algorithm, which is n-square complexity, this means we can send small inputs that are going to result in huge amounts of computation. So that's if there's like a REST API that exposes a quadratic complexity algorithm, that's a bug. Also iterating over sets with user controlled size. If at the endpoint that I'm hitting, there is a for loop which goes over a set where the attacker controls the set, then this set can be made arbitrarily large, and then at some point one request will mean 1,000,000 iterations over the set. So that's also a problem. Also, crypto operations, they consume a lot of CPU, and it's important to have a bound on how many crypto operations can be executed with little network usage. Yeah, there's also unlimited memory or disk store issues. So there is unconfirmed transaction pool. It's called mempool in Bitcoin, and this was also a problem. It would be possible to just send transactions that never get confirmed, and the whole network starts caching these transactions endlessly and runs out of memory sometimes. And also there is Orphan transaction pool. So now, yeah, I'll just kind of breeze through this since I'm kind of running out of time. Orphan transaction handling. So there was an interesting DoS vector in Bitcoin which involved orphan transaction handling. If we recall how Bitcoin transactions look like, it have multiple inputs and multiple outputs. Inputs are basically hashes of previous transactions, and indices of outputs in these transactions we're spending, and outputs are new coins that we are kind of creating. Not creating new coins, we're just transferring coins into new places. So what's an orphan transaction? Orphan transaction is a transaction that where an input is unknown. So if someone sends a transaction that refers to a previous transaction that's not on the blockchain, it's unknown, that's an orphan transaction. And Bitcoin has to keep these transactions because this is a peer-to-peer network, and the order of transactions is not guaranteed. So that's an orphan transaction. So now how does Bitcoin handle these transactions? Well, first of all, there is like a map orphan transaction map, which is just like mapping hashes of transactions into transactions themselves. So it's just a map, so that's reasonable. However, when someone sends a regular non-orphan transaction, this transaction may be referring to actually the parent transaction that an orphan transaction is missing. So in that case, the transaction needs to be unorphaned. So yeah, if we have an orphan transaction, that means one parent transaction of that orphan transaction is missing. And if there is a regular transaction, then this regular transaction may be the parent that we're missing. So there needs to be a procedure for unorphaning transactions. And we could try going through this whole map here and identifying which transactions need to be unorphaned, but that's inefficient. And also the number of orphan transactions here is really user controlled. If there is no bound on the number of transactions, then the problem is that there is DoS vector hidden in there. So I'm running out of time. I will not spend much time here anymore. The idea is, the problem is, how do nodes delete orphan transactions? It comes down to deleting edges in this graph, and the number of edges is user controlled. So basically, you send a lot of weirdly formatted, you send a lot of transactions, which creates a weirdly formatted map, which looks basically like this. And then when the node needs to delete a transaction, that's also kind of remotely triggerable, then the node needs to go over 1 million edges here to properly delete that transaction, and that yields a DoS. And let me see if I fix it. Okay. So yeah, going back to auditing cryptocurrency software, if you want to do that, there is a lot of non-templated bugs in this area. Some of the things have been seen for the first time, such as these net split attacks and the requirement of equivalence between node implementations. If we have a small divergence between the Python and a C++ implementation, that's a bug. So I'm not sure if that kind of situation has been seen before. Yeah, pick your own favorite coin and familiarize with the issues and in these areas that Bitcoin went through, and try to find them in your favorite coin. Yeah, I think these are references. I'm happy if anyone wants to collaborate on this. I'll be happy to do that. Yeah. Okay, that's it. Thank you.